What if I told you that every time ChatGPT gives you an answer, it is literally guessing? And not in the, oh, I might be wrong kind of way. I mean structurally, architecturally. It has no choice but to guess. Now, every word it produces is the result of one question. What comes next? 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 It's like asking someone to solve a, let's say, Rubik's Cube by only being allowed it to describe in just one color at a time, left to right, and never going back. Now, there is a completely different class of AI models that doesn't do this. Models that actually don't predict, but are more models that verify. Models that ask, does this make sense, rather than what's likely next? And these are called energy-based models, or EBMs, and they might be the most underrated idea in all modern AI. I will take the next 18 minutes to show you what EBMs actually are, why they're fundamentally different from large language models, and why there is a person who is very close to a Nobel Prize physicist who just quit academia to build one. Let's go. And of course, don't forget to join the Data Science at Home Discord channel. Link in the description of this video, and of course on the official website datascienceathome.com. This is where I hang out between episodes, so come find me. All right, so the LLM problem. To understand why EBMs are interesting, we need to understand what LLMs are actually doing under the hood. And I've spent already a number of minutes or episodes on this show to explain what large language models actually do. But I will try to make this self-contained. So, of course, if you need to expand your knowledge, feel free to listen to the previous episodes and, of course, follow the links that I typically share in the show notes. Or come on Discord because that's where we are, and we're always happy to chat. So, a large language model at its very core is a function that takes a sequence of tokens and outputs a probability distribution over the next token, okay? So probability of y given x, and that's pretty much what it is. That's the whole game, right? So you train this on, a very large amount of texts, enough text, for example, from the internet, from books, doesn't matter where you scrape this information from. And these models get very, very, very good at predicting what words tend to follow other words. And that's really impressive. We all know how impressive these models can be. Because these models are capable now of producing fluent, coherent, and also useful text. Many people are using to, make stuff, right? Even to code, even though they shouldn't rely on that. But okay, more on that another time. You know my opinion about all these things, okay? Now, there is a structural problem, which nobody explains, of course, because it's quite technical. That is the problem of the softmax. So the structural problem is a mathematical issue that these models have. So the softmax output is always non-zero, right? For every token in the vocabulary, there is always some even tiny probability mass. It's not zero, it's very tiny, but it's not zero. And so the model cannot say, I don't know. It can only say this token is very likely or this token is very unlikely to follow this context. Okay, but it must pick something. They are forced by nature. These models, these large language models, are forced to spit a token, the most likely token, after a certain context. And this is why hallucination isn't actually a bug, but it's not even a training failure. It's what the architecture is about. Okay, you can patch it. You can do reinforcement learning with human feedback. You can do RAG. You can do all the mechanisms that you can put in place to mitigate the problem of hallucinations, but you cannot remove it. Okay, you cannot make a next token predictor model refuse to predict the next token, right? That's what these models are. Now, there is another problem, which is called fixed compute. And that's even more subtle than the first. The first, once you are aware it exists, you accept the fact that there will always be an hallucination. There might always be an hallucination, okay? But then there is another problem, that every token gets the same amount of processing, whether the question is, what's 2 plus 2, or prove whatever mathematical theorem, I don't know, the Fermat's last theorem. The same number of transformer layers, you have the same forward pass, you have the same compute budget that is utilized to perform that particular prediction, okay? So, of course, we added chain of thought to fake more compute, but it's still just more tokens, okay? And then the third point that I want to make is that large language models are forced into language, okay? Everything must be tokenized, everything must be expressed as text. Why is that? It's because they come from text, they've been trained on text. This of course has a lot of consequences. For example, trying a large language model to plan a robot physical trajectory in 3D space, well, you will get a description of a trajectory, but not the trajectory itself, right? So text and tokens are the only currency that these models utilize, right? Now, let's switch to what EBMs are. Now, energy-based models. The core idea is, in my opinion, very beautiful because it's simple and it comes from physics, which is also a beautiful thing. So instead of modeling P of y given x, right? The probability of a token given a context, okay? The probability of an output given an input, more generally speaking. You model E of x and y, okay? What's E? E is the energy of a configuration, right? And I put that in the slide. Low energy means compatible, okay? High energy, of course, means incoherent. So what does that mean? Well, it means that E of x given y, or E of y given x, depending how you're reading that, is high when x and y are incoherent. So when essentially, let's say the token that would come after a context is highly unlikely, well, then you have high energy. And when it's very likely, so the probability, like the equivalent in probability terms, when it's very probable that that token comes after a certain context, well, then the energy would be very low, which is beautiful as an idea because it looks like, an effort. So think about what is the effort for the model to, let's say, accept a very incoherent token after, or a word after a context. Well, if the effort is too high, it means that that word must be really incoherent with the context, don't you think? So it's very logical as it works. Now, of course, it's not just logic, it's physics, because this probability, as I report in the slide, P of x, is proportional, this sign means proportional, to the e to the power of negative energy. So the exponential of minus e of x. So you have to think this as a landscape, and you can look at the figure here. So you have valleys, which are regions where the model has learned are real, consistent and plausible, while mountains are incoherent configurations, okay? Are implausible configurations. So data lives, of course, in the valleys, and nonsense lives in the peaks. Now, there is this is kind of a simplification, of course. There's much more than that. There is derivatives. Let's skip all that stuff. I'm just giving you the 10,000 feet view of this methodology. Now, this is where it gets really different, okay? In a large language model, inference, as we all know, is a forward pass, okay? Input goes in, tokens come out, right? While in a EBM, energy-based model, inference becomes an optimization. So you start with a candidate answer, maybe random, typically random at the beginning, maybe can even be a large language model's output, because these two things, as I will explain later, can coexist. And then you descend the energy landscape until you find a valley. Remember, the valley is where things are plausible. And you get y hat, which is typically the predicted version of y, which equals the argument that minimizes the energy. Okay, so it's the argmin over y of exy, of the energy of xy. So basically, what that means is that you are finding the y that minimizes the energy. Okay, that's the predicted y. So you are not actually generating; you are more verifying and refining. Okay, that's what you're doing. So the model is asking essentially, is this answer compatible with what I know about the world? Okay, and it keeps asking that until the answer stabilizes, which is beautiful, don't you think? Because it's not predicting a token, it's more about verifying that the generated token that someone else has generated maybe verified that the energy is indeed minimal, which means that it's plausible as an answer. Now, I'm going to be honest with you about why EBMs were hard to train for a long time. And this is another technical reason, which is called the partition function, Z. Okay? So to turn energy into probability, you need something that is called normalization over all possible configurations. So Z is equal to the integral of the exponential of negative energy over the x, okay, over the entire input space. If you find this difficult to follow, for those especially who are listening from the podcast, feel free to jump on the YouTube, because there is a very interesting slide there that explains and shows exactly that that integral, which is very simple, but essentially is an integral over the entire input space. Now, this is mathematically intractable, okay, which means that to make it tractable, it means that you can enumerate all possible states. And of course, you cannot. You cannot enumerate all possible states. That's why this is intractable, right? Now, this is the dirty secret, kind of, because EBMs are essentially unnormalized models, okay? They are models that are not normalized. You can compare the energies, but you cannot compute absolute probabilities without Z, right? Now, there are three approaches that mathematicians and physicists have come with, and statisticians have definitely come with, that try to crack this unnormalization problem. And these are contrastive divergence, noise contrastive estimation, and Wick regularization. So basically, in the first one, in contrastive divergence, you push energy down on real data, up on a Markov chain Monte Carlo sampled fantasy points, let's say, and Z cancels in the gradient. Noise contrastive estimation, or NCE, which reframe as classification, essentially asks the question, is this real data or is this noise? And then Z becomes a learned parameter, this absolute probabilities over all possible states. And finally, we have the Wick regularization. So this constrain the latent space volume, so the model essentially cannot cheat by assigning low energy everywhere. I will explain more this methodology later. But this is in fact LeCun's preferred path and the foundation of JEPA. JEPA is that model that I explained in another episode that you will find the description. You will find the link in the description. It's one of the methodologies to approach the concept of world models. Okay. All right. So let's have a look at. Now that I mentioned JEPA, I want to make some kind of comparison. So if you watched a previous episode about JEPA and world models, and of course if you didn't, go do that now. There is the link in the description. You already know that Jan LeCun has been pushing back against the large language model paradigm for some years now. So his argument is very simple. Large language models are trained on language, which is a compressed, let's say, lossy representation of reality. They model symbols. They don't model the world. And so what Jan LeCun wants to do, he wants AI to learn like a child does by interacting with an environment and building an internal model of how things work, and not the textual representation of how things work, which is what LLMs do, right? Now, JEPA, which stands, and I remember, the Joint Embedding Predictive Architecture, is the answer to all this mechanism. And at its core, if you think, JEPA is an EBM, is an energy-based model, okay? And this is kind of the energy function of a JEPA model. So essentially, the energy function E of xy is equal to the norm 2, this symbol here is norm 2, of sy minus the prediction of sx given z. What does that mean? I'm going to explain. Well, sx and sy are the encoded representations of context and target respectively. Okay? If you follow the previous episode, this would be absolutely clear. It's nothing impossible. It's absolutely basic and easy to understand. Okay, so you have the representation of the context, the representation of the target, and what you're saying here is like, hey, give me the prediction given the representation of the context and the latent variable z. Latent variable can be an action, can be whatever. You predict the next state, the state after that action, okay, and you make the difference between that, what you predicted, and the encoded representation of the target. So this measures essentially how far from the target you are. Okay, and if you are in a planning scenario, is essentially a bit like in reinforcement learning. It tells you how far you are from the target, from the goal, after you execute, after you performed a certain action from a certain space. Okay. That's why the difference and the norm 2. Now look at this, because if we convert this into energy, low energy, if this number is small, what happens is that you have low energy. And low energy means that the predictor successfully forecasts the target representation from the context. And if that energy is large, you get the point, right? Now, the key point is that everything happens in representation space. And we said that last time, that's JEPA in action, okay? It doesn't happen in pixel space or token space, but in representation space, which is an embedded version of the world, is an encoded version of the world. So the encoder can essentially discard anything that's unpredictable. Think about if you're in the world, the texture of a leaf or the exact path of a raindrop, okay? It's information that it's too detailed, an encoder would definitely skip because they don't contribute. First of all, they are very difficult to predict. And second, they don't contribute to, let's say, understanding where I can be, in which state of the world I can be after I perform a certain action. Okay, maybe knowing that it rains is more than sufficient rather than knowing the trajectory of all the raindrops, don't you think? Okay, so the big danger in JEPA, and of course all EBMs, all energy-based models trained this way, is collapse. And I already mentioned this at the beginning of this show. If essentially the energy of X and Y is equal to 0 everywhere, well, then you have found a trivial solution. Okay, remember, the model wants to stay in the valleys. It wants to minimize energy as much as possible, to have more confidence about the prediction. Now, there is a problem with that the model can trivially perform, find a solution when energy is 0 everywhere. That's a trivial solution. So every configuration has low energy. The model becomes useless because, has a 0 effort. So there is VICREG, which is that mitigation technique that I mentioned, the third one. VIC stands for variance, invariance, covariance, and REG stands for regularization. So indeed, it's called variance, invariance, covariance, regularization. It's quite hard to remember, but yeah, it's like that. Now, this form of regularization prevents exactly that. It forces the encoder to spread representations across the full latent space, so it cannot cheat by mapping everything to the same point, right? So the model has to actually learn the structure. It's forced to learn the structure of the world in order to minimize energy. Now, here I go with the person who actually started all this, because this is getting practical now. Let me introduce Eve Bodnia, a physicist, PhD in quantum information and algebraic topology from Santa Barbara, UC Santa Barbara. She published something like 22 papers on dark matter and quantum mechanics. I have not read these papers. I didn't have the time. Her thesis advisor won the 2025 Nobel Prize in Physics. You know, she needs an introduction, especially for people who are not technical, but actually she doesn't need an introduction. So now what she did is essentially that she quit academia while 8 months pregnant to build an EBM company. All right. So that's the kind of conviction we are talking about here. Now, and Jan LeCun happens to be on the board of that company. So the company is called Logical Intelligence. You can check that up. The model is called KONA, K-O-N-A, and Jan LeCun is the founding chair of the technical board, right? So it's a little family. Everything stays in the family. That's fine. Now, KONA is pitched as the world's first energy-based reasoning model. It's an EBM that reasons in abstract Latin space rather than language space. And the interface with the large language models is just one output channel. The reasoning itself happens in a completely different mathematical space, the embedded space. And here is the brutal comparison between the two. It's the number that makes people stop scrolling for sure. In a public demo playing Sudoku, Kona solved a relatively complex Sudoku game, which is of course reasoning task, by burning something like $4 in compute. The estimate for equivalent frontier LLM compute, $15,000. So now why is that? Is because energy-based models inference converges, right? And it descends to a valley and then stops. While large language models generate tokens until you stop them, okay? So you pay for every single generated token. Right? An EBM can allocate more compute to hard problems and less to easy ones. And it can do this dynamically. That's also the key difference between the two. Okay? That's called adaptive compute at the architecture level, not the prompt level. Remember, when we do that at the prompt level, the large language model that we hit is still using tokens as a currency. Okay, so the compute in the transformer architecture doesn't change at all. It doesn't matter if you're optimizing outside of the large language models. Once you hit large language models, once you hit the transformer architecture, that thing will start computing stuff, regardless of the problem, the type of problem, and the difficulty and the effort that you should put for that particular problem. Now, Bodnia's speech to the enterprise world is pretty simple. She said, well, and that's also what I think, there are many situations where you should not accept hallucinations. We have covered some of this, of course, in other episodes on this show, the so-called critical scenarios, okay? If you hallucinate while you are advising me or recommending me a movie to watch and you make a mistake and you hallucinate, the movie doesn't even exist, that's fine, it's kind of acceptable. But if you start hallucinating on patient records for healthcare, drug dosages, surgical planning, or defense, and you start bombing schools, children's and stuff, or hospitals, that's not acceptable. Or autonomous vehicles, if an AI piloting at 300 kilometers per hour, I don't know who drives that, but for planes, for trucks, for cars, you get the point, right? Or even finance. So these are the problems that, for which hallucination is not acceptable. And so that's why these are the problems for which energy-based models might play a very important role. Because now, if you have a model that allows you to verify, that can show you the energy is too high for certain predictions and very low for other predictions, well, it means that you have a direct measure of how wrong or right that prediction can be. And so that's very, very interesting. And now, if you want to run a comparison, I made this table here where I compare directly EBMs to large language models, and it's kind of a, repeating what I said in this episode. So if we take the hallucination as a dimension, okay, large language models hallucinate structurally, okay, while energy-based models can assign, as I said, high energy to incoherent outputs, and you can set a threshold or something and reject them simply when the energy is too high, right? If you look at the compute, large language models use fixed compute per token. As I said, once you hit the transformer architecture, there's no distinction between what is what, right? While EBMs use adaptive compute, which means more steps for harder problems, because they will try, they will stay in the mountains, in the peaks, and they will try to go down and will try to, put more and more effort until the energy goes down. Multimodality. Large language models need everything tokenized. Remember, the currency of large language models is the token, is the text, is the token, in fact. While EBMs can attach energy function to pretty much any latent space. It can be physical, can be logical, can be visual. So the multimodality, of course, can be achieved also with large language models, but with EBMs, it's kind of native, right? Multimodal outputs. Large language models collapse to one prediction or a blurred distribution of the token or the tokens, while EBMs can maintain multiple energy minima. So this means multiple valid solutions simultaneously. The training dimension, large language models train with clean MLE, while EBMs need Markov chain Monte Carlo, NCE, or other forms of regularization, which is historically harder, I have to say. Of course, maximum likelihood estimation here, the MLE, is more mature as a metric, something that people can understand. Markov chain Monte Carlo, NCE, or other form of regularizations are computationally harder to perform. But of course, the field has caught up in a way, and it's improving in that. And finally, scalability. Large language models have been scaled to hundreds of billions of parameters. We know how much energy they burn, of course, but they can be scaled to this number of dimensions or parameters. While EBMs, of course, they're very new. They haven't yet, and that's kind of an open question and open research. So we'll hear a lot of novel things on that side. So, what do you do with this? Well, if you are a developer or an architect making AI infrastructure decisions, I think there are a few takeaways here. Of course, I'm not saying that large language models will disappear tomorrow. They're actually not going anywhere. For language tasks, conversational AI, summarization, code generation, even though you have to pay attention to that, don't let large language model write your code and without even reading what it is. Try to understand what it does, what it generates. But it's essentially, they're exceptional for these things. For text-related things, they're okay. So use them. But if you're building something where correctness matters more than fluency, okay, where the cost of a wrong answer is measured in money or even worse, in lives, okay, well, then you need a different architecture. You need something that verifies rather than predicts. So, of course, with this said, EBMs are not a replacement, okay? They are a complement. The reasoning layer that large language models structurally cannot be. So what logical intelligence calls, they say deterministic AI for critical systems. And that's, in my opinion, a beautiful summary of what these things are, especially when they are combined. So, of course, if you want to go deeper, there is a few references that I collected for you. You will find some of the links in the description here. And of course, as I said, come on the Discord server. There is also a link down in the description. Of course, everything is on the official website, datascienceathome.com. There is Jan LeCun's 2022 paper, A Path Toward Autonomous Machine Intelligence. It's the canonical EBM/JEPA reference. It's free on open review. I read that paper. It's a very nice read. very approachable. It's not super easy, but it's not impossible. Okay, you need to. But I think that after this course, after these 2 episodes, well, 3 episodes, we have two on word models, part 1 and part 2, and this one. After these 3 episodes or less, you will have a much better way, and it's going to be a lot easier to understand the paper, A Path Towards Autonomous Machine Intelligence. Then, of course, we have logical intelligence. They have a blog. There is a post, The Art of Knowing, written by Yves Bodnia directly. It's very short, worth reading. And then there is a course materials on EBMs, also free, by Jan LeCun, New York University. It's all here. Now, next week, we'll talk about something else, but I don't want to spoil it, so I'll see you next time. And of course, don't forget to join the Discord, link below. See you there.